What's up, guys? Welcome back to another review session here as we continue to prepare for our final exam. This is the third of our series of videos where we will take a look at mostly some short answer problems incorporating some graphing and other items. So let's jump right into some examples. Problem number 30. Problem 30 says, given y equals r of x shown in the graph to the right and the tables below, answer each of the following. In part A, it says to evaluate f of r of 1. So this is a function composition. In order to evaluate, first, I need to examine the input of f, which would be r of 1. So r of 1 can be found by taking a look at the graph. This is r of x on our graph here. And r of 1 would correspond to an x value of 1 on the graph. And I have this point 1, 2. So r of 1 is equal to 2. Because this is a function composition, I'm going to take 2 and substitute that into f. Because r of 1 is equivalent to 2, f of r of 1 is the same as f of 2. So f of 2 would then correspond to one of my tables here, where the input value is 2, giving me a corresponding output value of 19. So f of r of 1 is 19. In part B, it says find the values for x. So there's a little spacing error there, but find the value for x such that the inverse of r of x is equal to 5. Now this is an inverse equation. So the y on the inverse is 5. Remember, inverses take x and y coordinates and switch them. So basically what I'm looking for is a corresponding value that would be r of 5. The x value on the graph would be 5. So I have this point 5, 2 on my graph. So the y value is 2 in this location. On the inverse, that would become the x value. So x would be 2. The same concept can be carried over to C, where we need to evaluate the inverse of g of 1. So here I'm looking for a x value on the inverse that is g, which would correspond with a y value on our regular function of 1. So I can find that point on the table where y is 1, and this would be equal to an x of 2. So g, the inverse of g of 1, is also 2. Taking a look at some graphing here in problem number 31, it says for each of the following, algebraically find all solutions for the given polynomial. Then sketch a graph of the function and show your work. This graph, or this equation here in 31a, could be put into the calculator, but because we have to find some algebraic solutions, I'm going to do that first and then check my answers. There is a typo on this problem. So let me adjust this. We could potentially do this problem, but I wouldn't expect you guys to be able to or have to do so on a quiz or on your final exam. Let's create this to something a little more student friendly. So let's change this 128x into a negative 12x there. So just a small adjustment to make this a more doable problem. So 31a, r of x is equal to x to the fourth minus 2x cubed plus 6x squared minus 12x. One of the things that I'm going to need to graph is the y-intercept. Remember, the y-intercept is r of 0. Or substitute 0 in for x. So if I substitute 0 in for x here, I'm going to get 0. So I'm going to get an x-intercept that is also my y-intercept at 0, 0. So I'm going to go ahead and plot that point. Now, algebraically, if I want to find the solutions, I need to find where the y values are 0. And probably the easiest way to go about doing this is to factor r of x. So if I go ahead and factor r of x, I notice that it does have a GCF of x, which would leave me with x cubed minus 2x squared plus 6x minus 12. And then I can factor this a little further. If I look inside those, inside the parentheses here, I can group these and then work at factoring by grouping. So if I factor inside of there, my first group that I have in the brackets, the GCF of that group is x squared, which would leave me with x minus 2. The GCF of the second group would be 6, which would leave me with x minus 2. So remember, I can combine coefficients into factors. So now factors are x squared plus 2, and x minus 2. and this would be for r of x. So if I want to find the zeros for r of x, I can set each of these factors equal to 0. X equals 0 is one solution. Sorry, this would be x squared plus 6 as I take the coefficient of 6 and place that there. So then I would have x squared plus 6 equals 0, which I could subtract 6 to get x squared equals negative 6, and x equals the square root plus or minus the square root of negative 6. I square root both sides, so x equals plus or minus I root 6, which is a solution, but is not going to show up on our graph. And then I would have x minus 2 equal to 0. So x would equal positive 2. So on my graph here, I have the x-intercept 0, and now I have the x-intercept 2. So now I need to finish with my graph. Now, as you recall back from the polynomial unit, what we looked for were x-intercepts, y-intercepts, and correct in behavior, as well as the pattern in between. So turning points we didn't necessarily find, but we wanted to make sure we have x-intercepts, y-intercepts, correct in behavior, in shape. In behavior, this is an even degreed polynomial, so both ends are going in the same direction. It is positive, so it is going to go up to the right, and if it's even, both go in the same direction, so it would go up and up. So our graph would look something like this. Now, again, we didn't find the turning point, and I notice I didn't even label the y-axis, but this would be the generalized shape of the graph. Now, I can go ahead and type this into the graphing calculator, which I have typed in. Let me get that typo out of there. I have typed that in, and I can look at my graph here, and we can see what we're looking for is correct in behavior and correct x-intercepts, and we have those. So our graph here does look similar to the graph on the calculator, and so we have the right solutions and graph. Let's take a look at another one. This one is going to be a little bit more complicated. As we take a look at q of x, I'm going to go ahead and start with just some graphing features. We notice that, again, it's an even degree, so ends are going to go in the same direction. It's a positive leading coefficient, so it's going to go up to the right because it's positive leading coefficient, even, so both directions are going to go up. Now, we do need to find other information in order to graph it. That information would be the y-intercept, which we can find by taking q of 0, substituting in 0 for x, which would give me negative 45. So my y-axis isn't labeled. I'm just going to go ahead and put a point on here and label this as negative 45. To find the x-intercepts, I need to factor this polynomial. This polynomial cannot be factored using our generic methods of like grouping or binomial distribution or any of those frequently used methods. It's a quadratic and it's an odd number of terms, 5 terms. So what we're going to use is the possible rational roots theorem. So in a previous problem, we went over the possible rational roots theorem. Factors of the constant over factors of the coefficient. The coefficient is 1, so just factors of the constant. So we would have 1 and 45. We would have 3 and 15, and we would have 5 and 9, the factors of 45. These are my possible rational roots for the problem that is given, or for the equation that is given to us. So one of these has to be a 0, and the one I'm going to check first is 1, because 1 is quick to check. I can just kind of basically go through the process of substitution, but combine all the coefficients. And if I combine all the coefficients and the answer is 0, then x equals 1 is a 0. So what I can do here is I can use x equals 1 in synthetic division to simplify that polynomial. So I'm going to use synthetic division looking at the coefficients 1, negative 2, negative 20, 66, and negative 45. My x equals 1 is my 0, so I'm going to go through the process of synthetic division, adding down columns and multiplying by 1 out here, and putting that result in the next column. And as I do that, I find that I have 0 as a solution here. So x equals 1, or 0 is a remainder, so x equals 1 is a solution. So what I would be left with then would be x cubed minus x squared minus 21x plus 45, which I might look at this and think factoring by grouping, which is not going to work out in this case. And so I'm actually going to have to repeat the process of synthetic division. And so I want to find another 0 here. Basically now I'm down into, I could try -1. If I wanted to try -1, I would switch the signs of all the opposite, or all the odd degreed coefficients. So 1 plus 2 minus 20 minus 66 minus 45. -1's definitely not going to work. So now I kind of need to go into a little bit of almost a guess and check method, or you could try to use your graphing calculator to evaluate or find another 0. In this case, I'm going to try 3. So I'm going to complete the process of synthetic division with 3 here. And as I do so, I notice that 3 is 0. So now what I'm left with is x squared plus 2x minus 15. And this I can factor. So this would factor into x plus 5 and x minus 3. So if I want to rewrite q of x, I can go ahead and rewrite q of x as a full factored equation. I wouldn't necessarily have to do this, but I can. What I get is the factor x minus 1, which gave me the 0, x equals 1 here. Add the 0, x equals 3 there from a factor x minus 3. There's another x minus 3, so this would be x minus 3 squared. And so this would be the entire factored version of q of x. So if I solve for my x's, x equals 1, x equals -5, and x equals 3, by setting each of those factors equal to 0 and solving for x. So what I want to do here is I want to go ahead and plot these points on my x-axis. So I would have a point at 1, a point at -5, 1, 2, 3, 4, 5, there's -5, and a point at 3. Now one thing to notice here is that 3, this came from a factor that was squared, so my graph is going to bounce at 3. So it's going to touch 3 and turn and change directions, continuing up to the right as we have that end behavior. It's got to change. It's got to go through x equals 1. It's going to go through our y-intercept, and then it's going to turn around and it's going to come through x equals 5. And there we have an example of what the graph may look like. Now I've saved us some time and I've put the equation into the calculator, and I'm going to go ahead and take a look at the graph. Again, my y value is, or my y-axis is not to scale, but here we see pretty much the graph that we drew up there. So algebraically, we found the zeros. We used some information about end behavior and intercepts to then sketch the graph. Let's take a look at another example problem. This example problem is again about graphs, but it's done entirely on the calculator. It says use a graphing utility to find the solutions to the below systems of equation. If the system has a solution listed as an ordered pair, x, y, work is not required on this problem. We're going to do it on the graphing calculator. However, I am going to need to do a little bit of work because I need to be able to input both of these equations into the graphing calculator. So my second equation on the list, we'll call this equation B. My second equation on the list can be input directly as it already has y by itself. Equation A cannot yet be put into the calculator because y is not by itself, but I can get y by itself by square rooting. Now remember, if I do create a square root in the process of getting a variable or rewriting an equation, it's going to create a positive version of the square root as well as a negative version of the square root. So I need to make sure in my graphing calculator I input both of the two roots, both a positive option and a negative option, and then I can look at my calculator, my graphing calculator. So there is the line from equation B. Equation A was actually a horizontal parabola here, And we do see that it appears to intersect. If I zoom in a little bit better, I can there see that it intersects on the bottom portion. It intersects somewhere in this location over here. And I can find that by doing second trace intersect. Going to move my cursor over semi-close to the intersection. Hit enter. It's going to put it on the second curve. I need to find that. Find where that cursor went. There it is. And it puts it on the upper portion of the parabola, but it's actually intersecting on the lower portion. So I'm going to push the down arrow key. So now I'm on the lower portion close to the intersection. And then I'm going to hit enter twice. And now because of how the distance I was from the intersection, I'm going to get a very, very slightly rounded answer. And that rounded answer would be 1.5, -1. So we can find the intersection in the calculator, and that is our solution. Problem number 3 talks about some graphing, but it's going to bring in some different information here as well. 33, excuse me. It says the quadratic function f of x has a domain of -4, x is between -4 and 8, greater than or equal to -4, and less than or equal to 8. And a range of y is less than or equal to -1. If the function h of x is defined by the equation h of x equals -1/2 f of x plus 3 minus 4, answer each of the following. So in part A, we need to list the transformations of f of x in the order in which they are applied, and that's to get h of x. Now remember, based on the notation that we know, the first thing that we look for is horizontal shifts. So we do have a horizontal shift. Inside the operation, or the parentheses in this case, in addition or subtraction is a horizontal shift. This is a shift, and we need to make sure we not only to identify the transformation, but to describe it. This would actually be a shift left 3. Remember, inside the operation, it is x minus h on the standard form. So first thing is a shift. Then we look for dilations and reflections. Their order can go in either way. So we can do dilations first or reflections, doesn't matter because they're both multiplication. So here we see a multiplication of 1/2. And so this is actually going to be a shift. It's going to be a vertical because it's outside of the operation or the parentheses. It's going to be a vertical compression because it is of a value less than 1. And so vertical compression by 1/2. We also have this negative out in front, and so this is going to be a reflection. This is a vertical reflection, or if you say that it reflects over the x-axis, would be vertically, this would be okay as well. Finally, the last thing we look for is vertical shifts, and we do have a vertical shift. This is a shift down 4. Outside of the operation is vertical, and it goes true to the parentheses or the direction that we see. Now, what we need to do is not only identify these transformations, but determine how they affect the domain and the range. So let's first start with the domain. The domain is x is greater than or equal to -4 and also less than or equal to 8. So what we need to do is we need to identify anything that's going to affect the domain. This would be any horizontal movements. In this case, we have the one horizontal movement that we have is a shift to the left 3. So a shift to the left 3 would be a subtraction on the x values. So we can subtract 1 on the x values, and so we would get -5 is less than or equal to x, which is less than or equal to 7. And this is going to be the new domain. Let me order these real quick. So we did the first operation, and it was the only operation that affected the domain. The others are all vertical, and so they're going to affect the range. So the range is y is less than or equal to -1. First thing that I'm going to do is apply the vertical compression and reflection at the same time. Both of these can be done through multiplication. A multiplication of -1/2. Now remember, when you multiply an inequality by a negative, it's going to reverse the direction of that inequality. So we want to make sure we're doing these operations in order, and so we would need to multiply first here, do the vertical compression and reflection. Now we can shift down. So the shift down would actually be a subtraction of 4. So 1/2 minus 4 would be y is greater than or equal to negative 7/2 or negative 3.5. Let's go ahead and take a look at another example problem here. In problem 34, it says to algebraically determine the function, or determine if the function f of x equals x squared plus x minus 4 is even, odd, or neither. Well, remember the relationship for inverse functions. If I take f of negative x, and that is equal to f of x, then this is even. So if the y values are the same, regardless of whether the x values are opposites or, if the y values are the same when x values are opposites, this is an even function. An odd function gives opposite y values when x's are opposites. So if I put in f of negative x, or the opposite of x, this would be the opposite of f of x. So what I need to do here is basically just figure out what happens when I substitute in a negative x. So if I substitute in the opposite of x, or negative x, I would have negative x squared plus negative x minus 4. So this would give me x squared minus x minus 4. And so now I'm going to compare these two functions. Well, all the terms are the same, but we have some signs that change and some signs that stay the same. So one of the signs changes here for x, and the other signs stay the same. So the opposites are not equal, but the opposites are also not, the opposite x's do not give us opposite y's. So what I would be looking for is either all of the equation to be exactly the same, that would be even, or the equation to have the same terms but opposite sides for each term. Neither of those things are the case, and so this would be neither even nor odd. So we want to substitute in the negative x and compare the signs of the coefficients. Let's take a look at two more problems here, and then we will wrap this series of videos up. Problem 34 says to algebraically determine the solution to the below equation. So there is a couple of different ways that we can go about solving this equation. Sorry, I believe I have another typo here. Let's go ahead and let's correct this problem. This is actually going to be e to the x power times e to the third power. So let's fix that. That's going to make this more in line with what we have done this year. So a couple of different ways that we can go about solving this problem. One of the methods here is to use our properties of exponents. So because I have two bases that are being multiplied, I can add their exponents. So this would be e to the x plus third power. Now if I have e cubed over e to the negative 2x power, these two bases are being divided, so I can subtract their exponents. So this would be e to the third minus negative 2x. Now notice here that both of these two bases are the same on the opposite sides of the equation, so I can use the uniqueness property to set their exponents equal to one another. And I'm going to simplify as I go along. So x plus 3 equals 3 plus 2x. Subtracting 3 from both sides and subtracting x from both sides, I get x equals 0. So 0 for x would be the solution to this equation. Problem 36 says to algebraically determine the domain for the below function. Remember with logarithmic functions, to determine the domain, the only consideration of the function that we have is the input value for the logarithm. So this input value must be greater than 0. So in order to solve this, we can start by subtracting 4 from both sides. So negative x squared has to be greater than negative 4. And then we can take this, divide by negative 2, or negative 1. So x squared has to be less than 4, and square root both sides. So as I square root both sides, x, remember this creates a positive and a negative case. X would be less than 2, or x would be greater than, and x would be greater than -2. Now remember, again, as you square root both sides, that creates a positive negative case. And as I change this to a negative, I switch the sign, I need to switch my inequality. Another way to do this is to consider the equation for the quadratic, that is the input. So a negative x squared plus 4, if we were to sketch that graph out here, would be, our intercepts would be -2 and +2. And it would look something like this. As it's negative, it would be open down. So we would want to see, where is this graph greater than 0? If we go back to the original statement, where is the graph greater than 0? Well, that is between -2 and 2. So our official domain here would be any place where x is greater than -2 and less than 2. And this is a good place to stop this series of videos. For more problems, go ahead and take a look at part 4 of the video series. As always, thank you guys for tuning in, and I'll see you soon.